So here we go, Lagrangian float. What Lagrange comes from is, Lagrange is a mathematician that considered changes along the trajectory. So that's why these floats are called Lagrangian, because this guy who first studied Lagrangian, these so-called trajectory. So now, how do you simulate it? So the properties that the float has is actually a location, the starting point. Okay, like in this example, you have an x location and a y location. Okay, and you have a float number. Okay, you might, for example, use 1,000 floats. Okay, and this I here refers to the number of your floats. So you want to, for example, focus at float number 33, then you just use 33. Okay? And the n again gives you the time level. This is your time level. So if the location doesn't change, your float will not go anywhere. You can, exposed to a current field, predict the displacements. Okay? Horizontal displacements. And displacement is a simple thing. Just time step times velocity tells you how much, what distance you will be moved. Okay, and this is what the displacements, how the displacements equations look like. Most basic form. Okay, and again you have two components. Okay, location is a vector, a horizontal vector has two components. You can split it up into two components, two equations, one for x, one for y, another one for y. And you have u and v in here. And this is the horizontal velocity at your location. And that might be become a little bit more complex, because you're moving from one grid to another grid cell. You might have to use a interpolation techniques to actually specify the horizontal velocity at your location. Okay, but you can see here it's an iteration. And you can place floats into actually changing variable flow fields as well. So that's okay. Now you can, let's have a look at it. How does that look? Here's one picture of these floats. Picture of Lagrangian float. Doesn't tell you much because there's no movement in it. There's no movement, but we can actually look at the movement. Let's have a look at this simulation. Here we go. Here are the movement of your floats. You can see this is the prediction. You can see even which regions are the fastest. It's the top view of your lake. You can see that there is actually some trapping zones. You can see that if you place floats on the island, they will never move. And some problems might arise if a flow strands comes too close to the, see that they're stranded. Okay, so you can reveal some more of the details of the dynamics using these floats. And the last point that I want to mention is you can actually also create an image of the so-called trajectories. I mentioned this word before, but it actually connects the pathway of a flow. You can draw a line like a dot to dot exercise. No, you don't connect these dots here or floats. Just for each float, you determine the path. And if you do that, you get images like this. You can see the history of the flow path. And in this example, you can see that there are two circulation cells. Okay, so one goes, this one is anti-clockwise around the island. You have even one path which stays on one side of the island. You have a larger loop which goes around the island. And you have one here on the left side, which moves clockwise, okay, around this part. Okay, and then you can actually imagine that you might even have a random disturbance, and you could actually move from one side to the other, become trapped in one part of the. So it's quite useful to do these trajectories, and you learn a little bit more about uh, regions which are even totally isolated. For example, if you're in the middle of this you might call the mini gyres, if you like, in this region here, where the mouse is now, it's no island. It's in the open lake here. If in this region, you might not move at all. Okay? In contrast, there are fast-flowing parts where you're exposed to very, very strong current. Okay, this is what we call trajectory.